Hey everybody, happy Wednesday. Good to see you again. Today we are going to go through 2.3 and 2.4. That sounds like a whole lot because we've never done two topics in one day before. But both of these topics are pretty short and they're pretty simple. So it made sense just to kind of smush them together and we'll go through both of these in the next half an hour or so. Couple things of note, your homework topic 1 for Unit 2 is due tomorrow, Thursday night. By midnight. I have it closing at 11:59. So please be aware of that. The questions on homework topic 1 are related to the first two topics, 2.1, which we had talked about last week Thursday and Monday, Monday of this week, and topic 2.2, which we ended up talking about yesterday during our live class. So be aware that if you're looking for help or if you're trying to understand how to answer some of those questions, the 2.1 videos and the 2.2 video from yesterday are still out there and posted on It's Learning. So topic 1 is all on that stuff, and again, that's due tomorrow night at midnight. All right, so let's talk about 2.3 and 2.4. 2.3 is about the structure of ionic solids. So yesterday we talked about the energy of bonds, right? We talked about intramolecular forces, as I called them. So we have covalent bonds, and we have ionic bonds, all right? So today we're going to look closer at how ionic compounds are formed, or what their structure is, right? How does that work, all right? We're also going to talk about 2.4, which is the structure of metals and alloys. That'll be a very, very quick topic, and it's pretty intuitive stuff. Really, all you're going to need to know from 2.4 is a couple of definitions and how to identify those, and you'll be good to go. And it's pretty simple. All right, so the learning objectives. We want to represent an ionic solid with a particulate model that is consistent with Coulomb's law and the properties of the constituent ions. So AP loves to use big words if you haven't realized already. The word particulate is implying particles. All right. Coulomb's law, we've talked about that quite a bit more now since we've jumped into Unit 2. Again, Coulomb's law is this, this mathematical approach of quantifying attractive force, right? How strong is the attraction between two particles? All right. And that's depending upon the magnitude of those charges and the distance of those particles as well. And we talked about that at the end of class yesterday too. Let's see, 2.4, represent a metallic solid or an alloy using a model to show essential characteristics of the structure and interactions present in the substance. Fear not, 2.4 is very, very simple, okay? All right, let's get into it. So, ionic compounds. An ionic compound such as sodium chloride doesn't form like you might think, all right? They are unique in the way that the ions arrange themselves. Unlike covalently bonded molecules, for example, water, ionic compounds do not exist as individual molecules. Instead, ionic compounds form lattice structures of alternating cations and anions. Okay, so a couple things. I would want you to underline this because that's really, really important. All right? When we read out the formula of NaCl, like we do, right? Right there. That's an ionic compound. It's a metal and a nonmetal. It's an ionic compound like we're used to defining from last year. But here's the deal. NaCl, sodium chloride, doesn't exist as little pairs of Na and Cl together. And there's another little pair, and there's another little pair, and they're all just kind of these, one-to-one, one sodium, one chloride bonded together. That's actually not how it exists at all. Ionic compounds instead exist in what are called lattice structures. This thing, all right? So this you can think of as like a grain of salt, okay? It's a cube, right? But think of this as a grain of salt. On your paper, obviously, it's, gray and other form of gray, so it's not great to look at. I'm hoping my purple and green spheres look a little more clear. But essentially, this is what sodium chloride would look like. It would be millions and billions and trillions of sodiums and chlorides alternating in this three-dimensional pattern, this three-dimensional lattice structure, as it's called. Now, so the question might be, well, why do we write it as NaCl? If there's actually trillions of these sodiums, shouldn't we have sodium subscript a trillion, chlorine subscript a trillion? Well, I mean, you kind of could, I guess, but essentially ionic compounds are empirical formulas, you can think of it as. They're reduced, all right? This is the actual structure of sodium chloride. And the formula we write to represent that essentially is a ratio. This is showing a 1-to-1 ratio in this lattice structure. And I'm saying the word lattice, not lettuce. Okay, we're not eating, well, I guess you can eat salt, but that kind of backfired. You get my point, okay? Anyway, so these smaller ones, the purple ones, would be sodium 1 plus. These bigger ones, the green ones, would be chlorine or chloride 1 minus. All right? And again, this is unique. This isn't what water does. Okay? Water actually exists in discrete little molecules. If I have a cup of water, what I have in that glass is a whole bunch of those H2O molecules. 2 hydrogens with an oxygen in the middle, 2 hydrogens with an oxygen in the middle, so on and so forth. Okay? So covalent molecules exist exactly like the formula is written. Ionic molecules do not. Ionic molecules exist in these crystal lattice structures, these three-dimensional repeating patterns, and the formula that we write is the ratio between the atoms. Okay? All right, so because of this unique structure, ionic compounds exhibit different properties than covalently bonded molecules. When ionic compounds are dissolved in water, the ions of this structure will dissociate. All right, so the next slide we'll look at this a little closer, but essentially, again, this picture is representing an ionic compound. Okay, and the next paragraph, if you're reading through that, is essentially saying exactly what I said on the last slide. Okay, but anyway, so let's look at how this would break apart in water. All right, that's what this last sentence up top is saying. When you dissolve these in water, this compound or this structure is going to dissociate. Okay? When the ions of the salt dissociate in the water, this allows the solution to conduct electricity. Substances that conduct electricity when dissolved in water are known as strong electrolytes. Okay, really, really, really important here. And this will come back later in the year full force, but let's talk about it just a little bit right now. Okay? Ionic compounds. Run out of space. Sorry. That's awful. Let me try again. Take 2. Alright, that's a little better. Ionic compounds. When dissolved are strong electrolytes. Okay? When you take an ionic compound and you dissolve it in water, it is a strong electrolyte. That is a huge deal, and it's a big concept, and it's going to come back. All right? You probably don't quite get what the heck I'm talking about yet, but let me give you a little context right now and a whole lot more context later in the year once we start talking about equilibrium again. Okay? So I have salt. I can take salt, I can put that in water, and it will dissolve. Okay? What actually happens when you dissolve an ionic compound is this. Okay? So here's my picture again. This was the same sort of representation that I had for the green and purple spheres in the last slide. Instead, now I have green and like these tan circles. Again, we're going two-dimensional on this slide, but this grid of green and tan pluses and minuses are trying to represent the ionic compound like I was trying to in the last slide. All right? Here's what happens. I've got a whole bunch of waters. These little Mickey Mouse looking guys. Those are waters. Okay? Oxygen in the middle, 2 hydrogens on either side, H2O. That's the formula of water. When I take my ionic compound and I place this in water, the water molecules, which have partial charges, if you remember from topic 2.1, right? Every single one of these water molecules has a partial negative near the oxygen and partial positives near the hydrogens. Okay? And as a result, when they get near the ionic compound, there's attractive force. I can have a whole bunch of water molecules surround the anion. Here's a negative ion, an anion. And the water molecules are going to orient themselves so that the partially positive hydrogens are facing that negative ion. Well, that should hopefully make sense, right? Negative charge, positive charge, they're attracted to one another. So the partial positive hydrogens on our water are very strongly attracted to the negative charge of our ion. On the opposite side, we have cations too, right? This ionic compound has positive ions as well. And the water molecules will surround the positive ion with the oxygens facing towards the positive cation, because the oxygens in our water molecules are partially negative charged. Again, negatives and positives are attracted to one another. So when you dissolve an ionic compound, this is what happens. This whole structure more or less just gets ripped apart by the water. Okay? And the anions, the negative ions, are surrounded by water molecules with the hydrogens facing it, and the positive cations are surrounded by water molecules with the oxygens facing it, because of the opposite charges of those two things, right? This is negative. All of these hydrogens are partial positive. This ion is positive, and all of these oxygens are partial negative. And this is how ionic compounds dissolve. Now, when this happens, it conducts electricity. Okay? And I have a question here. Does pure water conduct electricity? And the answer is not really. Not really. It's certainly not well. Okay? It doesn't, essentially. But the other problem with that question is typically you don't come across pure water, right? If you take water from the tap, water from a pitcher, if you have like a filter pitcher in your fridge or something like that, there's always ions dissolved in there. You are not drinking pure water from any source that you're drinking water from. There's always stuff dissolved in there. It's very difficult to get rid of all of the stuff that is dissolved in water. All right? It's not a high percentage. It's not like when you drink a glass of water out of the tap, it's like 70% water and there's 30% of stuff dissolved in there. No, not at all. It's literally 99.9 something percent water, and there's just a couple straggler ions that are just impossible to get rid of, more or less, okay? But here's the actual truth. So pure water doesn't really conduct electricity. All of the water you come into contact with isn't pure, all right? So when people tell you to get out of a pool when the thunderstorm's coming, yeah, please get out of the pool, because, spoiler alert, that water is going to conduct electricity because there's stuff dissolved in the pool water, right? So don't take my water doesn't conduct electricity speech as like reason to swim during a thunderstorm. Don't do that. That's not safe. Anyway, so just another side note, because I'm on my tangent already. Purity of water is actually verified or tested by using electricity. So when scientists are trying to determine how pure a substance or a sample of water is, they'll pump electricity through it and measure that. If less electricity passes through, that means it's pure water or closer to pure water. So I think that's kind of an interesting thing to think about too. But anyway, all right. So ionic solids, as a result of this structure, are very brittle. Okay. For example, the best example is salt, right? Table salt, sodium chloride, because you're familiar with it. Okay. So you can take a grain of table salt and just smash it, right? And it'll break. It's very, very brittle. It'll break right apart. It'll crumble. It'll shear, and you can make a whole bunch of smaller salt chunks, right? It breaks very nicely, especially if you take if you have any of like that sea salt or like the bigger grain stuff, right? Take a little grain of that bigger sea salt and smash it, and it'll break. It's very easy to smash. Okay, so ionic solids are brittle. All right. And I have another statement here. Ionic compounds are sometimes simply referred to as salts. These two terms, this term and this term, okay, these are the same thing for our class. If you hear the word ionic compound, it's a salt. If you hear the word salt, it's an ionic compound. Now, please be careful. When I say salt, I don't just mean sodium chloride. I mean any ionic compound, okay? So, for example, magnesium fluoride, that's ionic. It is a salt, all right? So, there's an insane amount of different ionic compounds that exist, and they are all classified as salts. So if you ever hear the word salt, your brain should immediately go to ionic compound, and vice versa. Okay, so don't let that term salt confuse you. It's any ionic compound. Okay, so anyway, so this little representation of these pictures are trying to show why ionic compounds are brittle. Okay, so you see that we have like a little grid of 2, 1, 2, 1. The 2s would maybe be cations, the 1s would maybe be anions. It doesn't really matter. But here's the point, right? When you have this nice structure, if nothing's disturbing it, we have all of these attractive forces, right? Look at this one right here. That's maybe a negative charge, and the 2s around it are all positive. So there's all this attractive force, positive, 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 and a negative, right? It's perfectly surrounded, it's symmetrical, it's nice. But when we introduce a stress, okay, like let's say I push the top sheet to the right and I push the bottom sheet to the left, all of a sudden now my alignment of my grid is going to have negative, negative, positive, positive, negative, negative. And that introduces repulsion. And as that repulsion occurs, we're just going to cleave these layers. We're going to break them, right? And this is why ionic compounds are brittle. They're nice if they're not disturbed because we have this beautiful alternating pattern with a bunch of attractive forces at play. But with some stress, or again, if you were to take a little salt crystal and smash it, that's the stress, you're going to cleave it, right? It's going to break, it's going to shatter. They're very, very brittle because as that stress is introduced, you're aligning negatives and positives right next to each other, which creates repulsion, and they break. All right, so that's all I got for ionic compounds. Okay, this is 2.3 at the end of 2.3 right here. Big takeaways are this. Ionic compounds do not exist as individual molecules. They exist as these big structures, these lattice structures, okay? When I say a formula for an ionic compound, this is representing the empirical formula. This is a ratio. For every 1 sodium in this structure, I have 1 chloride in this structure, okay? Other big takeaways. When ionic compounds are dissolved in water, they are strong electrolytes, meaning they conduct electricity. Pure water does not conduct electricity. Ionic compounds are salts, and they're very brittle. However, they have very high melting points, okay? If you tried to take some salt, put it in a pot, and then put it on your stove, you're not going to melt that salt. Not going to happen at all. Okay, your stove is not hot enough to melt table salt. However, if you took that same pot, put a bunch of sugar in there and turned on your stove, it will melt the sugar. So be aware of that. Ionic compounds have very, very high melting points too. It's another property. All right, let's go to metals. So metals, we previously learned from topic 2.1 that metallic bonds are unique. Okay, when metal atoms come together to form a solid substance, the atoms pack tightly together and the valence electrons are all of these atoms are free to roam about the structure in what is known as a sea of electrons. So metallic elements can also be mixed to form what are known as alloys. So an alloy is a mixture of 2 metals. All right, and there's 2 types of alloys that you need to know. These are the 2 definitions that you need to understand for topic 2.4, and this is pretty much it. All right, we have what's called a substitutional alloy, and it's probably exactly what you'd think it is. We are substituting one metal for another metal. This happens, okay, this happens when one atom, or when atoms are similar in size. Okay, in other words, one atom replaces or substitutes the other. Okay, so here's an example. I have copper, I have zinc. This makes brass, by the way. Okay, so your instruments downstairs if you're in band. Not all of them. I'm sorry if you play a woodwind or, other, I don't even know what else is in a band. Drums of sorts or, percussion of sorts. I apologize. But if you play a brass instrument, it's this. It's a mixture of copper and zinc. And copper and zinc are very, very similar in size. Their radius is almost the exact same. So when I mix copper and zinc together, I can create what's known as a substitutional alloy. Essentially, if this were pure copper, right, these 5 silver ones that I have here would all be the same coppery color. But when I introduce zinc, the zinc atoms more or less just replace the existing copper to create an alloy. All right? Another type of alloy that you need to know is called interstitial. An interstitial alloy occurs when the atoms are different sizes. Okay, one atom goes in between the other atom. This is iron and carbon. This is steel. Okay? The alloy of steel, which you come into contact with every single day, we have steel everywhere in our society, is carbon and iron mixed together. But iron is way the heck bigger than carbon. So when you mix these two elements to make an alloy, the little carbons fit right in between these little spaces of the iron atoms. And this is called an interstitial alloy. So again, the names are pretty nice here, right? Substitutional. What happens? Well, one substitutes the other. They're similar in size, and the second metal or the second element just replaces what was already there. Interstitial. The other atoms or the new atoms that we introduce go in between, okay? In the middle or in these little spaces, and that's called interstitial again. All right, so you need to know these two terms, and you'll be good to go on 2.4. That's the only thing I'm going to test on 2.4. That is it. If you can identify or know what substitutional alloy means, if you can identify or know what interstitial means, you're good. That's it. I've got a couple questions here to finish us up. But yeah, we'll wrap this 2.3, 2.4 up nicely. All right, so this is just a general thought process, right? What are some reasons why manufacturers would want to use an alloy over pure metal? Okay, think about that for a little bit in your head. If you want to pause the video to think about it a little longer, go ahead. But I mean, why? Why, right? Why wouldn't you want to use maybe a pure metal, for example? What could be the benefits or possible reasons? Reason number one, cost. Different metals have different values. Some are more abundant, some are more rare, and by potentially adding a more abundant element or a more abundant metal into a really rare metal, that could lower the cost, which is good, right? If you're a business, you want to lower the cost of your product and potentially have still the same aesthetic or the same functionality, right? So by putting some cheaper metal in with some more expensive metal to make an alloy, you could save on cost. Something else. Change the properties, right? For example, jewelry. If you had pure gold in jewelry, gold in its pure form is pretty malleable. You can scratch it, you can bend it. If it's thin enough, you can really mess with gold. So when you see a gold ring, there's other junk in there. It's not pure gold. They're adding other elements to lower the cost, but also change the properties, right? So rhodium, I know, gets used quite a bit. What else gets used? Rhodium is the big one, I know. Anyway, so an alloy in jewelry is potentially to change the properties from a flimsy, malleable gold, pure gold, into something that's more sturdy, so it doesn't just break and bend and fold over on you, right? Yeah, those are the two big reasons. Now, change properties kind of encompasses a whole bunch of stuff, right? The reason why you add carbon to iron to make steel is more rigid. It is stronger than pure iron. So again, that's another properties change, right? So there's all sorts of reasons. All right, metals are often described as being malleable, meaning that you can shape them and mold them. I was just talking about that. Based on the structure of the metallic bonding, why does this property of metals make sense? So with metallic bonding, Okay, if you remember, metallic bonding kind of looks like this. You've got all of these positively charged nucleus and core electrons of all of these metal atoms tightly packed in. And then throughout this structure, we have what's known as a sea of electrons. Okay, and what that is trying to imply is that the valence electrons are they're free to go. They are not trapped. They are not stuck or confined to one atom. They are free to move. And this is why metals conduct electricity. And as another result of this, the bonding between all of these metals is non-directional. Okay? So metallic bonding is non-directional. Meaning, I can smush this, I can shift this, I can move these around, and it doesn't really change the strength. And that's what malleability is, right? When I take, like aluminum foil, right? When I take aluminum foil and I crumple it up into a ball, all right? I'm moving these atoms around, but because metallic bonding is non-directional, I'm able to do that, right? It's not rigid, it's not tough, it's not hard. If you've ever experienced tin, we have a sheet of tin here as well. Maybe when you guys are back, I'll let you play with it. But it's a thick piece of tin, and you can just bend it and fold it, and it's the weirdest kind of experience. So metals are malleable because the types of bond, I missed a word, didn't I? Metallic bonding, is non-directional, okay? All right, if you're given two unlabeled samples of sugar and salt, what could you do to determine which is which without tasting them? So in a lab, we don't taste things. That's generally best practice. Please don't eat lab materials. But the question is if I gave you two white crystalline powders and I said, hey, one of those is sugar and one of those is salt. Can you figure it out without eating it? Okay. What could we do? Well, if I dissolve them in water, they're both going to dissolve. I'd have to do something else, wouldn't I? Okay. By the way, I'm stalling, not that because I know the answer, I'm just waiting potentially for you to think. But anyway, there's really two ways, or there's two good ways that we could do this. The first is try to melt them. Sugar melts at a much lower temperature than salt. Much, much lower. Okay. So if we run a melt test, or a melting point test, sugar is going to melt at a much lower temperature than salt would. Not even close. Kind of like I said earlier in this video, right? If you put a pot, or take a pot, put it on the stove, pour some salt in there, you're not going to melt it. Take a pot, put it on the stove, put some sugar in there, you're going to melt it. Okay, it's much more easy, or the melting point of sugar is much lower. The other way, and I kind of started going down this path, right? So dissolve them in water and check conductivity. When you dissolve sugar, there's no charges. When sugar dissolves in water, the whole molecule dissolves and is surrounded by the water molecules. But there's no positive and negative cations or anions. When you dissolve salt, you have cations, one positive, anions, one negative, floating throughout that solution. And as a result, sugar, when dissolved, will not conduct electricity in water. Salt, when dissolved, will conduct electricity in water. So these are the two big ways that you could do this. Just kind of a thought experiment. All right, I'm all done. Have a lovely day, guys. Please remember that topic 1 is due tomorrow night at midnight. If you have any questions, you need any help, please don't be shy. Pop into my office hours, and I'll be happy to help you. We'll catch you guys tomorrow for live class on Thursday. See you later.